Okay, so let's continue with our chapter electric current. So let's proceed to our new subtopic, which is current density. So current density has a symbol which is denoted as J. Okay, so for the definition of the current density, so current density is actually defined as the electric current which is I per unit cross-sectional area of the wire. So the current density is actually defined as the electric current per unit cross-sectional area of the wire. Okay, so if you wish to answer the question of the definition of current density, you should write it in the form of full sentence, which is the current density is actually defined as the electric current per unit cross-sectional area of the wire. Okay, so from the definition, I can see that my J, which is the current density, is actually equals to I over A, which is equals to the electric current per unit cross-sectional area of the wire. Alright, so as a note here and as the reminder, so my current density, is actually a vector quantity. So vector quantity, we know that which consists of magnitude, and at the same time we also have a direction. So magnitude, we know that it is a value. So the direction, okay, let me just drag it down. So the direction for the current density is actually same as the flow of electric current, which is I. So the direction for the current density is actually same as the direction for the electric current. Okay, so from here, from the formula, which is J is equals to I over A, so I can see that the J is actually directly proportional to the electric current. The higher the magnitude for the electric current, the higher the current density. Okay, so and there's another relation here, which is J is actually inversely proportional to the cross-sectional area of the wire. So the higher the cross-sectional area of the wire, the lower the current density. So the bigger or the higher the cross-sectional area of the wire, so the lower the, how should I say, the lower the size of the current density. So this is the relation. Okay, so we have done for the introduction for the current density. So let's move on to another relation. So we are still in the subtopic of the current density. So we're going to talk about the relation of the drift velocity. So the drift velocity is actually the net velocity of the free moving electron, as we discussed from the previous video. Relation of the drift velocity, which is bar V, and the current density. So what do we have what is the formula that we can prove there is actually the relation between the drift velocity and the current density? So this is J, of course. So remember from the previous video that we discussed about I is actually equals to NEVA. So this is the number of electrons per unit how should I say that? So this is the number of free electrons per unit volume. Okay, so this is the number of electrons per unit volume, and this is the electron, and this is the drift velocity, and this is the cross-sectional area of the wire, and of course this one is the current. Okay, so from this formula I can actually find out the relation between the current density and the drift velocity. So if I about to move this A to another side, so this is I over A, so this is NEV. So I know that I over A is actually the J, so J is actually equals to NEV. So I already proved that my J is actually has the relation with the drift velocity, which is J is actually equals to NEV. So I can say that J is actually directly proportional to the drift velocity. Okay, so we have done for the introduction and the theory. So let's move forward for some examples of some question. So I'm going to guide you how to answer the question for the current density. Okay, so for the examples, for the first examples, so let me see how much example that I have taken. Okay, so there's actually only one examples here. Okay, so let me just draw some of the diagrams. Okay, so this diagram should be our reference for answering the questions. So this is actually the direction for the electric current. So this is okay. So my mistakes. So there's actually two different sides of the wire. So I denote this one as my P and this one. Okay, so I denote this one as my P and this one is my Q. Okay, so this is my I. Okay, so this is my I, of course. So the information given here is actually the diameter for the wire P. So the diameter for the wire P is actually 12 millimeters. So 12 millimeters is actually times 10 to the power of negative 3 meters. So as for the DQ, so DQ we have 4 millimeters. So the millimeters is times 10 to the power of negative 3, of course. Okay, so find the, for the first question, find the current density which possessed by P. Okay, so J in wire P. Okay, so how are we going to find this one? Okay, so I actually missed one of the information. So the current given is actually 1.2 ampere. Okay, so find the current density in wire P. Okay, so we know that J is actually equals to the I over A. So regarded to this diagram, so I assume not assume, the question is actually provide this wire is in the form of cylindrical shape, of course, cylindrical shape. So the cylindrical shaped wires, okay, so the cylindrical shaped wire, the cross-sectional area that we know is actually the circle. So this will be the cross-sectional area. So the cross-sectional area is actually in the form of circle. So I can say that the cross-sectional area for my cylindrical wire P is actually pi r square. Okay, so I is 1.2 cos. So this is pi, and r is actually half of the diameter of the wire P cos. So this is, okay, let me just see for, so this is 12 times 10 to the power negative 3 divided by 2, since it is a half of the diameter. So if I calculate the value, so what I get is actually 1.06 times 10 to the power of 4 ampere per meter square. Alright, so this is how we find the current density. Okay, so as for the question B, so the question B is actually the current density which possessed by Q. Okay, so this is question B. J is wire Q, so this is J is equal to IOA, of course. So of course this one also the cylindrical wire, so cross-sectional area basically is the pi r square. So this is I, and this is pi, and this is, okay, so this is dq over 2, and this is square, so 1.2, so this is pi, and the diameter for the wire Q is actually 4 times 10 to the power negative 3, and this is 2, and square. So if I calculate it, the answer what I get is actually 9.55 times 10 to the power of 4 ampere per meter square. Okay, so this is one of the examples that how we find out the current density. Okay, so let's move on to the next questions. There's actually another example for the question of the current density. So let's move on to the second examples. Okay, so this is the second examples. So given the wire A and wire B, so the wire A possess the current density of okay, let me just, okay, so wire A possess a current of 2.5 times 10 to the power of 8 ampere per meter square. Okay, so this is the drift velocity of the free electrons. So okay, so this is the millimeter per seconds. So the millimeter, as I said, is times 10 to the power negative 3 meter per seconds. Okay, so that's another wire. So another wire which is B. So B has the current density of 7.5 times 10 to the power of 8 ampere per meter square. So the question is, what is the drift velocity which possessed by the wire B? Okay, so as we discussed just now, okay, so let me just write here. So as we discussed just now, the formula, which is NEV, So this is the relation between the current density and the drift velocity, which is J is actually directly proportional to the drift velocity. So this relation is actually talking about the higher the number of the drift velocity, the higher the electric current is produced. So the higher the electric current, so hence the higher the current density. So this is actually the express relation between the drift velocity and the current density. Okay, so if we have the relation here, so what we can do is actually find out the drift velocity for the wire B. So what we need to do is actually use this equation. So VB over VA is actually equals to the JB over JA. So VB is the one that we need to find. Okay, so the VA 0.16 times 10 to the power negative 3. Okay, if JA is 2.5 times 10 to the power of 8, and this one is the 7.5 times 10 to the power of 8. So if I calculate the value, so what I get is actually 0.48 times 10 to the power of negative 3. And this is meter per seconds, of course. Okay, so this is how we calculate the drift velocity for the wire B by using the relation of between the current density and the drift velocity. Okay, so I think that's it for the subtopic of the current density. So let's proceed for the new subtopics. So in this subtopics, we are going to talk about the electric conductivity and the resistivity. Electric conductivity and resistivity. Alright, so first of all, we're going to discuss about the resistivity first. Resistivity. So the resistivity, okay, so before enter the resistivity, we're going to talk about the definition of Ohm's law. So we have the Ohm's law. So the Ohm's law is actually states that the electric current, so the electric current is denoted as I, electric current flowing through a conductor, is directly proportional to the potential difference okay, so the potential difference is V cos across the conductor. So Ohm's law basically states that the electric current that flows through a circuit is actually directly proportional to the potential difference across the conductor. So the relation is actually V is directly proportional to I. So what we have here is actually the constant. So the constant what we have here is actually R. So Ri. So V finally is actually equals to IR. So this is what Ohm's law states. Okay, so let's move on to the resistance. So resistance. So what is actually the resistance? So the resistance, okay, so if we observe from the formula, so R is actually equals to V over I. So from this formula, I can directly find out what is the definition for the resistance. So in this case, my resistance is actually a constant. So constant, it means that it's defined as the ratio. So the ratio is actually our keywords. The ratio of the potential difference. The potential difference the ratio of the potential difference to the electric current in the conductor. Electric current to the conductor. So since the resistance itself is a constant, so the definition for the resistance is actually the ratio of the potential difference to the electric current. Okay, so this one is my mistake. So this one should be the word in the conductor. So this is the definition of the resistance. So after introducing the resistance, so we need to know what is actually the causes of the resistance. So the causes of the resistance. So what is the causes that will cause the resistance to the wire? Okay, so from here, the accelerated electrons okay, let me just see for a moment. Okay, so I think I should explain first before I write the whole sentence. Okay, so assume I have a wire. So this is my wire. So of course we know that the wire consists of the lattice atoms. So I just simply draw the lattice atoms. So this is the direction of the current. So we know that basically the flow of electron is actually opposite to the direction of the current. So this is the movement of the electrons, free moving electrons, with their own drift velocity. So when moving inside this, when the free electrons is accelerated by the electric field, of course, okay, so let me just drag it down. Okay, so when the electric field is supplied to the wire, so the electron is accelerated, as we discussed from the previous video. So the accelerated electrons will eventually collide. So this collide with the positive ions. So collide with the positive ions. So the positive ions or the lattice atom, which is the same, which is all acceptable. Okay, so collide with the positive ions and the lattice atoms. Okay, the collision. So the collision between the free electrons and the atoms before the free electrons scattered away by the lattice atoms. So the collision will eventually causes, okay, so the collision eventually will causes resistance. So from the previous video, we did discuss about the collision of the free electrons, accelerated free electrons, will causes the velocity of the free electrons to be decreased. So the decrease in the velocity causes the net velocity to be produced. So the net velocity will produce the electrical charges and finally will produce the electric current. So this collision not only will produce the electric current, but at the same time will causes the resistance. So this collision, so let me just write it down. So this collision will produce I, and at the same time will causes the resistance. Okay, so this is the relations between the electric current and the resistance. So the electric current and the resistance basically came from the collision of the free electrons with the positive ions and the lattice atoms. Okay, so this is actually the brief explanation. Okay, so let me just write it down for the full sentence. So what is actually cause of the resistance? What is the causes of the resistance? So the accelerated free moving electrons, so the accelerated free moving electrons due to the electric field, okay, collided with the atoms in the metals with the lattice atoms, which is more accurate. Lattice atoms, so I write it as lattice atoms, which is also acceptable. Okay, in the metal and scattered away. Causes resistance. So after colliding with the lattice atom and scatter away from the lattice atoms will causes resistance. Okay, so this is how the resistance produced. And of course, as we said that from the previous video, so the collision will causes the electric current and at the same time will produce the resistance. So we should not forget about the energy, the transference of energy from the free moving electrons to the lattice atoms. So the transfer of energy from the electrons to the lattice atom will cause energy to be transferred, and the heat energy will be transferred from the one end to another end. So the heat energy transfer will causes the temperature of the wire to be increased. Okay, so this is all the explanation. Alright, so let's move on to another. Okay, so let me just observe for a while. Okay, so let's move on to the factors affecting the resistance. So some of the factors also came from the features of the wire. So what is the factor that will causes the resistance? So for the first one, it's actually the length of the wire. So the longer the length of the wire, so the higher the resistance is the wire that process from the to the wire. Okay, so the first one is actually the length, and for the second one is actually the cross-sectional area for the wire. So the smaller the cross-sectional area of the wire, so the higher how should I say that, the more difficult for the electric current to flow from one end to the another end. So the difficulties of the flow of the wires causes the resistance. So I can say that for the first relation, the longer the wire, the higher the resistance. So the smaller the cross-sectional area, the higher the resistance. So this, for the second relation, is R is actually inversely proportional to the cross-sectional wire. So if I going to combine these two relations, so what I get here is actually L over A. So if I wish to find out the equation, so my equation is actually R is actually equals to rho L over A. Okay, so this is the rho L over A. So this is the equation for the resistance. So this rho is actually what we call resistivity. Okay, so the resistivity is actually defined as the resistance per unit length when its cross-sectional area is 1 meter squared. So the resistivity is actually defined as the resistance per unit length when its cross-sectional area is 1 meter squared. So this is the definition for the resistivity. Okay, so I think we should stop here now. So we will proceed the next of the other parts in the next video. So if there is any question need to be asked, please comment below this video, and I'll see you next time. Thank you. Bye.